Here we're going to consider a vent from a clothes dryer where air at 38 degrees C, and the reason we put the temperature there is that we need to look up air properties there, into the atmosphere. The vent is galvanized iron, and the reason we need that information is we need a roughness factor in order to solve our problem. It contains 6.2 meters of pipe, and what that means is that the length is 6.2 meters. We have 4 elbows. Each one of them has a loss coefficient equal to 1.5. The pressure at the start of the pipe is equal to 50 pascals. And we want to know the flow rate of the air if the diameter is equal to 100 millimeters. Finding the flow rate of a fluid cannot be solved by simple algebraic manipulation. And so let's look at our governing equations to see why. And we'll start with the basic equation, the energy equation. We're going to simplify this by saying that the vent is horizontal, and what that means then is that Z1 is equal to Z2. We're also going to say that the diameter is constant, and so what that means is that V1 is equal to V2, and finally it vents into the atmosphere, so that means that our P2 is equal to 0. So if we rearrange the equation, we can write it in terms of the velocity. Here our P1, as shown before, is equal to our 50 pascals. Everything else for the equation is given here, except remember that our gravity is 9.8 meters per second squared. So our sum of our loss coefficients is going to be equal to 4 times 1.5, which is equal to 6. However, we have this friction factor here that we need to solve for. So our friction factor is a function of the Reynolds number, where the Reynolds number is equal to the velocity times the diameter divided by kinematic viscosity. So note that the Reynolds number is a function of the velocity. So here's our plan. We're going to use Excel's solver on the Colebrook equation, which solves for the friction factor. If we can put everything in terms of F, the friction factor, in this equation, we can guess an F and use solver to solve for it. So our plan is to put velocity in terms of F, put Reynolds in terms of velocity, which is a function of F, put that Reynolds in the Colebrook equation, and solve for F. So let's put some numbers in. So using the numbers from the problem statement, we can solve for velocity in terms of F. So here we have the Colebrook equation that is only a function of the friction factor F. And so we take that equation, we go to Excel, we put it in solver, and we are able to solve for the friction factor. So here we're going to guess a friction factor of 0.02 and put that in this equation. We want it to equal 0, but if you note, and again here up here is where that equation is, we want it to be equal to 0, but with a friction factor of 0.02, it's equal to 1.26. So we need to use solver so that that number is equal to 0. So we go up here, we go to data, we go over to solver, and what we want is to set this cell equal to a value of 0 by changing this cell right here. And when we do that, we come up with here a number that is virtually 0 with a friction factor of 0.029. So what do we do with this friction factor? Well, we put it back into our expression for velocity. So when we put 0.029 back into this expression, for our friction factor, we're able to solve for our velocity, which is equal to 3.37 meters per second. But be careful, the problem statement asked for the flow rate. So what we're looking for is Q, which is equal to the velocity times the cross-sectional area, which is equal to 3.37 meters per second times pi d squared over 4. And our final flow rate, Q, is equal to 0.026 meters cubed per second.